Hi, this is Jeff from the Ozark Mountains in Missouri, USA.
In part 1 of this 2-part series, we learned about DIGIs, what they are, how to create them, and play them on your Commodore 64. We also learned about a physics professor whose curiosity led to a breakthrough in speech synthesis in the 1970s. If you haven't seen that video already, the link is in the description down below. In this video, which is part 2, we're going to go into the nitty-gritty detail of the Cruncher software, which is the C# code I wrote to take our output from Audacity and convert it into something our C64 can handle. Likewise, we'll do a deep dive into the DigiPlayer software on the C64 itself. We'll see what makes it work and a few variations that were created along the way. We'll also take a look at the compression schemes I tried, see what worked, and we'll see what didn't. Well, let's get started. Thanks to PCBWay for sponsoring this episode. Whether you need a small simple board like this or a larger, more complicated design, head on over to PCBWay.com, click on PCB Instant Quote, upload your files, and select from the plethora of options available. PCBWay offers a wide range of products and services, including assembly, stencils, and PCB design. When you have a need for circuit boards, head on over to PCBWay.com and give them a try. In part 1, we used Audacity to record our speech sample, filter it to just the frequencies between 300 Hz and 4000 Hz, which encompass human speech. We normalized it to take up the full volume range, and finally we exported it as a signed 8-bit file at an 8 kHz rate. Remember, we need our sample rate to be at least twice as high as the highest frequency we want to reproduce. This is called the Nyquist value. As you might recall, the next step after the processing in Audacity is the Cruncher program. And after we click the number 1 button and load in the file that we're going to work with, we're going to click the number 2 button to scale it. We'll first cover the concept in general, and then we'll take a look at the actual code behind each function. The file we exported from Audacity is made up of bytes, which have values from +127 to -128. In other words, a signed 8-bit value. The first thing we need the Cruncher to do is convert this data into an unsigned format, that is from 0 to 255. This process is fairly simple in concept. If we add 128 to every value, we will have shifted all of them up the number line, so they will fall within the range of 0 to 255. However, our sample data may not be centered exactly around 0, and it may not be taking up the entire +127 to -128 range, even though we normalized it in Audacity. For example, we might have a maximum and minimum values of 111 and -113. What I did was to first calculate a value that would center the data about 0. Then it was scaled to take up the entire +127 to -128 range, and finally, we add 128 to make all the values positive. This should result in all values being between 0 and 255. The exact reasoning behind my taking this approach now escapes me. Our Cruncher code has 4 main sections. We have all the methods that have to do with the user interface, those to do with the actual data manipulation, some miscellaneous helper methods, and those methods which were added on to create various log files for help in the development. If we look here in the user interface, we can find out how scale works. Everything to do with tbstatus.txt is just updating the status box to give feedback to the user. The first thing we do is call the findMinMax function, which takes the input file and returns the minimum value and the maximum value found within that file. We then can use that information to calculate the scaler to scale the file up to our full 8-bit value. And here's where we're creating that centering offset I mentioned earlier. And when we get down to the output file section, we are passing it the information we calculated above, and it will scale and output the file. Instead of going about things this way, I think what would have made more sense is to find the minimum and maximum value here. And then for the offset, we could have just used the absolute value of our minimum value. because if we added that to each of the values in the file, that would have resulted in the file starting at 0 and going up to somewhere close to 255, and then we could apply the scalar and be done. Both of these accomplish the same thing, but I'm thinking the second method would have made a little more sense. Future Jeff here. After recording this, I found a problem with my installation of Audacity, and in trying to track that down, I went ahead and modified the scale function to work just as I described previously. I also added the ability to the Cruncher program to accept both signed and unsigned 8-bit PCM files. We'll talk more about that later. This down here is just calculating the final min value and max value after we've scaled and offset the file. And again, we're providing more feedback to the user. Now that we have our data massaged nicely to fit in our entire 0 to 255 8-bit range, we need to reduce this to only 4 bits, which is the width of the SID volume register. Mathematically, this is a simple matter of dividing by 16. However, division is a glacially slow process on old 8-bit computers. Fortunately, we can easily divide by 2 by shifting all bits to the right. If we do 4 such shifts, we will have divided by 16, and very quickly at that. When you press the number 3 crunch button, the user interface section just looks at what is set in the output rate box here and calls the appropriate section of code. If we had selected an 8 kHz output, we'll go to the crunch 8 method. And we have some setup here, which is just amending our file name to reflect the process that we're doing. And we're creating an input stream and output stream to read and write the new file. This just has to do with the creation of a log file for debugging purposes. And then we get down to the heart of the matter. We read in each byte of the file, and we add whatever rounding value the user had set up. And we make sure that we have not gone over 255. And then we decide if this byte would be compacted to a low nibble or a high nibble, and we act accordingly. If it's a low nibble, we'll shift 4 positions to the right, and we'll save that, making sure that we do not go below 1. We don't want to ever set the SID volume to 0 because that'll create a noticeable distortion. On the next pass, we're doing the same basic thing, but we're going to save our data in the high nibble. So we mask off the low nibble. We'll make sure our high nibble is not less than 1, and then we'll OR together the high nibble and low nibble, and we'll write that out. Now let's touch on what the rounding value actually accomplishes. What you've probably noticed is that what we have actually accomplished going from 8 bits to 4 bits is to throw away the lower nibble and only keep the upper nibble. This means that whatever the value of that lower nibble was, it will have no effect at all on our 4-bit value. Imagine if this were an amount of money, say $10.99, but we could only record a whole dollar amount. Most of us would round this up to $11. By rounding up our 8-bit value before we crunch it to 4 bits, we allow that lower nibble to have some effect on the final value, and we'll come up to closer to the actual value than just by lopping off that fractional amount. As an exercise, add 4 to our initial starting value of 220 decimal, and then shift 4 times to the right, and see what the difference is between the final value that you get and that we're showing here. Even though we have packed our nibbles 2 to a byte, we're still using 4K of RAM per second of speech, which is sampled at 8 kHz. Is there a way we could reduce the memory requirements further? Well, the simplest way would be to reduce the sample rate to something like 4 kHz. I implemented 2 different types of 4 kHz downsampling. One just throws out every other sample, which is a very simple method, but it doesn't sound the best. The other way is to take an average of 2 successive bytes, and this is only a little more complicated, and it does sound better. While a 4 kHz sample rate does have the amount of memory used, it plain sounds awful. And while on its own it was a bust, it was not a completely wasted effort. It came in handy with one of the compression methods we'll talk about next. The first compression method I tried was RLE, that is, run length encoding. In concept, it is very simple. You count up repeated values and output a token to indicate the next value is an RLE pair. For example, we could take this 8-byte sequence, which has 12 successive 7s, and encode that as a 4-byte sequence. We use the 00 to indicate that the next byte is an RLE pair, and the C7 would indicate that we need C, that is 12, of value 7. Well, I got the RLE compression working and wrote an RLE decompressor in C# to make sure it worked. On the Commodore 64, it was too slow. It just took too many clock cycles to decompress. After going to all this trouble, it seemed like RLE might reduce the amount of data by around 20%, but it would result in a much more complicated player. However, this does have the advantage of being a lossless compression method. You get out exactly what you put in. I left the RLE code in the Cruncher program, but in the course of shifting things about, I lost the code on the C64 side of it. However, you can see how the decoding works, as there's also a decoder built into the Cruncher program. The next method I tried was interpolation. This method makes use of the 4 kHz downsampling we did above. However, it plays back at an 8 kHz rate and interpolates, or makes an educated guess, to calculate a value between 2 successive samples. In other words, it plays sample A, and then the average of A plus B, and then sample B, and so on. This sounds much better than a 4 kHz sample played at 4 kHz, but not as good as a real 8 kHz sample. The advantage is that it uses half the memory, or 2K per second of speech. At this point, we know all about crunching our sample data to make 4-bit samples and how to pack 2 4-bit samples into a byte for use with our DigiPlayer. Now we'll take a look at how the simple DigiPlayer works, as well as the version that will play a 4 kHz file with interpolation. To make the playback work, we need to play one of our sample nibbles every 1/8000th of a second, which is 0.125 milliseconds. Happily for us, the C64 has a very precise timer built into its CIA chips. We can configure CIA number 2 to generate an NMI, a non-maskable interrupt for us, at this precise time interval. An interrupt is an input pin on the microprocessor that lets it know that some other process needs to take control over the CPU. The CPU will finish the instruction it is on, save some particulars, and then jump to the address set up in the interrupt vector and start running the code that is there. Interrupts come in 2 flavors, maskable and non-maskable. We can tell the CPU to ignore a maskable interrupt. We might want to do this to let us finish a critical piece of code before releasing control. A non-maskable interrupt will be processed every time unless a previous non-maskable interrupt is still in effect. The DigiPlayer uses a small bit of code that runs as a non-maskable interrupt, running about 8,000 times a second. This alone uses about 50% of the processor power. We are leaving the screen enabled and change the screen color it is playing so we have something nice to look at. Our video chip, the VIC-2, will steal a few cycles here and there, but who wants to look at a blank screen? Because this interrupt code is running 8,000 times a second, every single processor cycle counts. Every additional clock cycle in your code amounts to 8,000 clock cycles per second. In situations like this, we can sacrifice code size to gain execution speed. In our DigiPlayer, the first thing we want to do is disable the maskable interrupts, and then switch out the kernel ROM. We don't want the Commodore 64 trying to do any of its normal housekeeping duties while we're playing a sample. The next thing we want to do is zero out all of our SID registers. On Vice, this will already be done for you, but on a real Commodore 64, when it powers up, these will all be in an unknown state, so we need to zero them out. This next bit of code works around Commodore fixing the volume bug on later SID revisions. We are setting up each of the 3 voices to be modulated as well. This will help make the Digi audible on newer SIDs, but is still quieter than on the original 6580 chip. Now we need to tell our C64 where our NMI routine lives in memory, so when the signal comes in, it knows where the correct code is to run. Then we are presetting the starting address of our sample data. We're using a self-modifying pointer to point to the sample. We'll go over that in more detail later. We also need to initialize the byte we're using as a flag to let us know if we need to play the high nibble or the low nibble of the sample byte. We are initializing it with a hex value of 55 here, which gives us a binary sequence of 0, 1, 0, 1, 0, 1, 0, 1. And the NMI will shift through this alternating sets of 1s and 0s for our flag. More on this trick later. We also need to preload our first sample byte. After all the setup is done, we can configure CIA number 2 to trigger the NMI at the correct rate and enable interrupts again. At this point, the NMI will fire at our preset time interval and run the DigiPlayer code automatically. When entering the NMI, the first thing we do is play a sample nibble. We do this to reduce the amount of jitter, that is the timing variation between each successive volume change. If there was a lot of jitter, it would affect the playback quality. We assume here that the nibble we need to play is always in the lower nibble. We have to do a bit of bit twiddling to make sure that when we set the new SID volume setting, we are not changing the upper nibbles of the same register. The next 3 lines are a very clever bit of code from Chromatics on the 6502.org forum. It shifts the flag byte, which we initialized as 01010101, to the left. If the carry flag is clear, that means we did not shift a 1 out. This is our cue to load a new sample byte. If we had just shifted a 1 out, that means we just played the lower nibble of our sample byte, and we need to shift the upper nibble down 4 places, which we do here. Once we do this, we're done until the next time the NMI fires. The load new block makes use of a self-modifying pointer. In other words, we are directly modifying the 2 bytes after the LDA to change the address within our sample data we want to read from. This saves a handful of clock cycles at the expense of a bit of complexity. This sort of code will also only run from RAM. This is a good case for the use of a self-modifying code, but it can be overused and lead to very hard-to-follow programs that break very easily when you make small changes. After loading a new sample byte, we increment our pointer with self-modifying code magic. Then we look to see if we have crossed a page boundary. Since we know our DIGI data takes up full pages of 256 bytes, we only need to check to see if we are at the end of our sample when we cross a page boundary. This trick saves a few clock cycles as well. If we are not at the end of the sample, we increment the high byte of our self-modifying pointer and then return from the interrupt. If we are at the end, then we branch down to stop and clean up after ourselves before exiting for good. Another suggestion from Chromatics on the 6502 forum was to use local exit code instead of jumping to a single exit point. This does use a bit more memory, but it saves clock cycles, so we're trading memory usage for faster execution. The compression method I tried that worked was interpolation. This is where we downsample our 8 kHz file to 4 kHz and make an educated guess in the player as to what the missing nibble would have been. I tried 2 different approaches to this type of player. Both versions are the same except for how we move between states. Interpolator A cycles through the 4 different states of playback by changing the NMI vector to point to the next state. Interpolator B uses a main NMI routine to play the next nibble and then makes clever use of the 6502 bit instruction to branch to the correct code based on the current state of decoding. This clever use of the bit instruction is once again thanks to Chromatics from the 6502 forum. The link to this thread is below. This is the Type A interpolating player. Our initialization is pretty much like the simple player. However, we have 4 different NMI handlers, labeled NMI Handler 0 through NMI Handler 3. We start off in a state of 0, so we would call NMI Handler 0. And then after it's done, we change the NMI vector to point to NMI Handler 1, etc. This lets us call the required code for each stage of interpolation without needing any comparisons, which would take more clock cycles, and it's also conceptually very simple. We're using 2 different self-modifying pointers this time. Load new is the pointer to the address of the current sample byte called A. We also need to take a peek at the next sample byte since we need to calculate the missing nibble between the 2. Peek next is the pointer to the address of the next sample byte B. We also have 2 bytes of 0 page dedicated to holding in-process data. We are calling these N0M and N0L, though I don't recall why. N0L always holds the next nibble to play in the low nibble position. As we read the current sample byte A and peek at the next sample byte B, we store the data in process in these 0 page locations and always move the next nibble to play into N0L. The first time the NMI handler is called, it will be to NMI handler 0. We play the first sample as we did in the simple player. We shift the upper nibble to the lower nibble position, just as we did before, and we're going to save that to the N0M storage area that we discussed earlier. And then we do the interpolation between the high nibble and low nibble, and we save that back in the N0L position to play next time. Then we finish up by changing our NMI handler to point to NMI handler 1. NMI handler 1 is very similar. We play the sample as normal. We move down the value we stashed before into the N0L position, and we change our NMI vector to point to NMI handler 2. When we move down into NMI handler 2 is where it starts to become a little more interesting. This is where we have to peek at the upcoming value in order to interpolate values. Other than that, it's basically the same as is NMI handler 3, and when NMI handler 3 is done, it's going to point back to NMI handler 0 unless we're at the end of our sample. The big difference in the Interpolator B version is that we are not changing the NMI vector. We jump to the same NMI handling routine and play the sample nibble in N0L. We make use of a counter to track the current player state, 0 through 3, and then use the bit instruction on the counter value. We branch to the correct bit of code to handle the particulars of each state. This clever idea was from Chromatics on the 6502.org forum. I'll link below to this thread. The first thing to notice is we're preloading our counter with FE instead of 0 as you might imagine. When we go down and look at the player, you can see that we're playing just as we normally did, and then we're loading the accumulator with a 1, and we're using the bit instruction on the counter value. We're going to branch positive to ISR handler 2, branch not equal to ISR handler 1, and if we go down here to ISR handler 2, you notice that we're also doing a branch not equal to ISR 3, so we've chosen all our 4 states using this one test. Let's look in a little more detail at what this bit instruction is doing. We preload our counter with FE to represent state 0, which might seem strange. Remember that the bit instruction sets the 0 flag as though the value in the given address was ANDed with the accumulator. In addition, the negative and overflow flags are set to match bits 7 and 6 respectively of the value stored at the address tested. This table shows each state, the counter value for that state, and what the registers look like after the bit instruction is executed. The first test we actually do is BPL, branch is positive, which will take us to ISR2. When we get to ISR2, then we're actually doing a BNE, branch not equal, which will take us down to ISR3. If we had dropped through BPL, we would have gone down to this branch not equal to ISR1, which is here, and finally we'll fall through to ISR state 0. Please note here that I've grayed out all the registers that the bit instruction does not alter. The ones in yellow we're actually concerned with for the test we're making, and we're not using the overflow flag at all. You don't often see the bit instruction used in 6502 code, but I thought this suggestion by Chromatics was quite brilliant, and it illustrates a very good use case. He also mentions that you can use the bit instruction to distinguish between 8 possible states or branches with this method. I'll leave it to you if you're curious to figure out how to go about doing that. I thought we would play back all the samples in one block to make it easier to distinguish between the 8 kHz sample rate played at 2, 4, and 6 rounding values and a 4 kHz sample rate played at 4 kHz and then played at 8 kHz with interpolation. The last sample is a 4 kHz rate that played back at 8 kHz through interpolation, but it accidentally has some zeros right at the trailing end, and you can hear the problem that causes.
Testing 1, 2, 3. 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 Testing 1, 2, 3.
While recording some new sound samples for this video, I noticed an odd problem. They all sounded horrible. And this kind of confused me because some I had recorded just a few weeks earlier still played back great, and I could process them with the Cruncher software and everything was fine. Eventually, I tracked this down to Audacity was not outputting signed 8-bit PCM files correctly, and this really confused me because I'd used it many times before. I noticed I was using Audacity 2.4.2 on my desktop, and I checked my laptop, and that still had Audacity 2.3.3 on it. And the laptop would output 8-bit signed files just fine. I originally thought, oh, this is a problem with the new version of Audacity, and that's going to be a big problem for people that are just downloading it to try to make digis. So what I did, thinking it was an Audacity problem, is I went back to the cruncher and I added the ability to use signed or unsigned files. You just click this checkbox right here if your file is signed. And then I modified the scalar section of code, as I mentioned before, which also made it really easy to incorporate using unsigned files. I also made one other change in the cruncher program dealing with downsampling to a 4 kHz rate. Now remember, when we're downsampling to a 4 kHz rate, we're taking 4 full bytes and crunching that down into one single byte. So we take 2 bytes, average them together, and we make one nibble out of that. We do the same with the second 2 bytes. But the problem was, if our input file didn't come out to an exact multiple of 4 bytes, we would wind up somewhere stuck in a state that was not the last state of 4, so we may not have actually calculated a full set of 4 bytes to come up with one single output byte. So to alleviate that problem, we calculate our output byte and we save it as last byte. And then we get down to the section where we're padding the output to come up to a full page. We just use that last byte value to pad with. And this took care of that problem. So this let me record some samples and save them as an unsigned 8-bit PCM, but I was still really confused about what the problem with Audacity was, and I joined the Audacity forum, and I had a really nice guy named Steve trying to help me out, and the thing was, it was working fine for him, and I was just super confused. It didn't seem to make any sense what was going on. And then I noticed that under Tools here for Audacity 2.4.x, there is a new option called Reset Configuration. So I clicked on Reset Configuration, and then magically my 8-bit signed PCM files were fine. Now I can only guess that there are some new bits of the configuration for Audacity 2.4.x that weren't in the earlier versions, and when I upgraded, those new settings weren't set to a proper default value. I really don't know what the problem was, but I would suggest that if you're just downloading 2.4.x, or if you notice any other problem outputting an 8-bit signed value, just reset the configuration, and then everything should be fine. Well, we sure have gone through a lot of code this episode, both C# code for the Cruncher software and 6502 assembly for the C64 itself. I hope my explanations were clear enough to allow you to jump in and start playing with it yourself. I've also never been accused of being stingy with comments, so I hope all the notes I left in the code will help make it clear what I was trying to do, even if I didn't do it quite right. All the software I wrote for this project is open source. The link to my GitHub repository is below. For the Cruncher code, I used the free version of Visual Studio 2019 with the installer project extension. The links to those are also down below. There's also a note on the GitHub page as to where to find the executable, so you can run that directly if you prefer. I had a lot of fun learning about digis, how to make them, and how to play them on the Commodore 64. I'm sure there's still lots of room for improvement. There might be other settings and other filters you can do in Audacity that would improve the quality. There might be other compression methods you could try to reduce the amount of data needed per second of speech. I hope this encourages you to experiment with digis on your own. Make some, play some back, and maybe incorporate some digis in your next C64 program. If you do, I'd love to hear from you. Leave a comment down below. As always, I'd like to take a moment to say thanks to the folks who help support the Hey Birt channel through Patreon and other means. If you'd like to find out more about becoming a supporter, just look in the description down below. There's some links there. Also appreciate everyone who subscribes to the channel and watches the videos. It's very encouraging to see that subscriber count grow little by little every week. If you have any comments or suggestions, just leave them in the comments section down below. I would love to hear from you. Well, until next time, bye.